Okay, why don't we go ahead and get started. Welcome everyone to Thursday DMICE conference. We're trying a little experiment today. Of course, I worried all night whether anyone was going to show up, and I'm glad to see there's people here. Anyways, what our experiment is that our group, our research group, really works as a group. So I thought rather than one person doing it, we would do it as a panel, although I note that our fourth panelist is not here yet, but hopefully he'll be here. Anyway, so we're going to talk today about work that we do, our regular project, funded by a couple grants, which I'll acknowledge on the next slide. And the focus of our work is reusing EHR data for various clinical tasks. In this case, two tasks in particular, cohort selection and rare disease surveillance. And we'll describe how we're going to do that. So our speakers are myself, Bill Hersh. I will then hand off to Steve Chamberlin, our postdoc, who probably most of you know. He was an NLM postdoc, and now he's a postdoc on this project. Aaron Cohen, a professor in the department, and when he gets here, Steve Bedrick, who is an associate professor in the department and also a PhD graduate of our program. So this work is funded by two grants. One of them is federal from the National Library of Medicine, an R01 that originated with Stephen Wu. Some of you may remember Dr. Wu, who was here and then left to follow his wife to do an ophthalmology fellowship. And Alnylam Pharmaceuticals, so it's also some industry funding, although we're really not working on their products per se, although we're developing methods that may enable them to better identify candidates for their products. Okay, so I'm just going to, actually let me go back. So I'm going to give an overview of our background and methods. We're each going to try to limit our comments to 10 minutes, which means I've already gone 3. I have 7 left. Steve is going to talk about the Cohort Discovery project, all of this at a fairly high level. Aaron, the rare disease detection, and then Steve Bedrick, some of the future directions for our work. So I think you all know that my research focus, since I was an NLM fellow way back when, has been in information retrieval. I've written a book on the topic. That particular edition is a little bit out of date, but there's a new one coming. And you've all done search, information retrieval, whether you go to Google or PubMed. We do it for different reasons. You might be looking for information on something. We focus on 2 use cases in this work. One is patient cohort discovery, so basically doing a search to try to identify patients who might be candidates for clinical studies. And then the second one is rare disease surveillance, looking for the presence of rare, often underdiagnosed diseases, in this case one in particular. There is a little bit of history of this. Actually, next week, some of you will be heading off to the AMIA meeting, me too, but before then, I'm actually going to another meeting called TREC, the Text Retrieval Conference, that is this annual challenge evaluation, mostly non-medical, but because of my and others' efforts, have always had a medical task in there, so a challenge evaluation for different research groups to compare their methods on a standardized data set. We actually had a medical records data set for what we called the TREC Medical Records Track a number of years ago. It's challenging with medical records because of all the privacy concerns. There was actually a de-identified data set from the University of Pittsburgh. It's no longer in widespread use for a variety of reasons. There's another one out there that some of you may have heard of called MIMIC, but it's been a real challenge for this kind of research because there are not readily shareable large data sets. Stephen Wu then was awarded an R01 from the National Library of Medicine. He actually moved here when and actually we were already collaborators, but he moved here because his wife came to do a residency in ophthalmology, and so he was on our faculty for the duration while she was here. And because he came from the Mayo Clinic, we basically do our methods in parallel. Although we can't share data, we can only share our methods and results. So there's a variety of ways that we measure success in information retrieval. You actually don't think about it explicitly, but maybe implicitly when you search. Am I finding everything I'm looking for? What's my recall? And are my results precise? Am I getting things about what I'm looking for? And those are the measures that information retrieval and many other fields use, called recall and precision. You can actually combine these two measures because sometimes you want an aggregate single measure. The simplest and most common way is the F measure that basically lets you set a proportion on whether you want recall to be more important or precision to be more important. Then there's some more complex aggregate measures, and the one you'll hear about with us, oftentimes for a variety of reasons, you may not have enough relevance judgments. So this BPREF measure is a useful measure when you have a lot of data that's not been judged. If you don't have the resources or the records are big, like in the case of medical records. So most of you in the room who are clinicians know what medical records look like. This is my weak attempt at art to try to show what a medical record looks like. And the kind of take-home message from this is that a single patient's medical record has a lot of elements, a lot of diverse kinds of data. Some of it's structured data, some of it is unstructured data, textual data, and it's challenging for a variety of reasons, not the least of which is that it needs to sit on a very secure server because the data in our case is from OHSU patients. And if you're like me, there's about a 1 in 5 chance that your records in the collection, I actually checked, mine didn't make the cut, but anyways, it may be in there. We have an IRB protocol and restrictions on who can access it, who can use it, and so forth. This is just a table of the different types. There's about, the original data set had 100,000 patients. We actually, for the Rare Disease Project, got some additional data, but it pretty much has a complete medical record, all the notes, problem lists, lab results, medications, hospital encounters, things like that. We get it in XML, and actually due to our former graduate, Brian Laraway, who now works for Oaktree, who was the analyst who helped us get the data after we received the IRB protocol. And the way that we judge the success, well, the way we judge how well our algorithms work, measuring that recall and precision, is actually having people. Steve Chamberlin's done some of that work. We've had other medical students, informatics students, others. And actually Steve Bedrick, who's here now, originally developed this interface to do different kinds of relevance judgments. And this is the one that we use for judging whether a patient should or not be retrieved, or either a cohort selection task or a rare disease like acute intermittent porphyria, which Aaron will talk about. And so this too is an it's a web application, but it's sitting on a secure server, and only people who are on the research team approved by the IRB can access it. So the use cases then for our work, as I've said, one is Cohort Discovery, which is offered these days by a lot of medical centers, including OHSU, but it's actually not been that well studied. There's not that many papers that people have published about how well it works. So one use case is, can we retrieve cohorts of patients, kind of like doing a search for specific clinical studies? Steve will give some examples of that, and then the rare disease detection work that Aaron will talk about. So I'm going to turn it over to Steve Chamberlin here.
Hello, everybody. I'm Steve. Thanks for. Is it, okay. So the arrows advance. Yeah. Okay. Okay. So the last year or so, I've been working on evaluating and comparing different methods for cohort retrieval using the EHR data, and this is. I put the list again of the different data types to emphasize that this is patient level. It's not data or document level, so that adds a level of complexity. We did this using the Cranfield information retrieval evaluation methodology, which Bill had described some of the components of already. So it requires a test set of data, which we've already talked about. We have about 100,000 patients. This is live data from EHR. And then we have to have topics that we search for in that data. So we've identified 56 topics or cohorts, which are actual requests that we've had either at OHSU or the Mayo Clinic, and I am one of the 100,000. And then we want to check. We want to test different methods. So we're comparing really two main categories of methods. We have word-based, what we're calling automated word-based queries. So these are strictly word-based queries. And then we have semi-structured Boolean queries. So the idea of the semi-structured is that that's our kind of our gold standard that we want to compare the word-based queries to. The word-based queries actually have different parameters that we varied. So there's 48 iterations for each topic on the word-based queries. And the other big difference between the two is the word-based queries are ranked, as we talked about. So those come with relevance scores, and they're ranked by relevance. The Boolean query is I didn't use SQL, but it's essentially a SQL query. So as the name says, it either matches or it doesn't. So there's no ranking in the list. And then we talked about the interface. So this is a clinically trained person goes in and actually assesses the different pools that we pull back from the different methods. And then just flags each patient as either relevant, possibly relevant, or not relevant at all. So, and we pulled, for the automated queries, we pulled random samples from for the 48 iterations for each of the topics. And for the semi-structured Boolean queries, we couldn't do all of them because of time, but we selected 10, and we did a full evaluation of everything returned for those. So then we take that data, and we use a program called Trekeval to generate the statistics. And for this analysis we did, I used only recall precision and bpref. And recall and precision don't require ranking, so those were good for comparing the Boolean queries to the word-based queries. And the bpref is a ranked statistic, so we use that more for evaluating the word-based queries and the variations across the different parameters. So the last thing we did is we got interested in decomposing a topic. So what characteristics in a topic might affect the performance, and also might affect what kind of a method you choose to query that topic. So we called that our topic taxonomy. These were structural or content-oriented. And then we did a predictive model. We did a beta regression predictive model with simulated data to try to look at is there some sort of interaction between these taxonomy characteristics and the methods that you select. So these are some examples of the topics. We had 56 again. These are examples, kind of a summary example and a more detailed example. And I'd mentioned that there are 4 parameters for the word-based queries, and these are the 4 parameters that were varied, and so all possible combinations equals 48 iterations. The first one is kind of important, the topic representation. The A version summary statement is kind of like what's in the right column, summary statement for the topic. B is an actual case study example for that topic. And then C is a detailed criteria. That's really the structured or semi-structured version. So that would have a lot of codes, ICD and CPT codes, and maybe some text. Text subset is, do we search just the notes or all the document types? So we're pulling back a lot of documents per patient, a lot of multiple documents from a data type, multiple data types, and those all have relevance scores. So we have to come up with a patient-level relevance score, and so we used a couple of different aggregation methods, and then the retrieval models themselves at the bottom. All right, so this slide, it's a lot of box plots, and this is just the word-based query performance, and this is all based on the bpref statistics. So I have 48 box plots, and each box plot is one of the 48 iterations for the word-based queries, and the box plot distribution are the 56 topics, distribution of the performance of the 56 topics. So I won't go into a lot of detail here. I think some of the main patterns, this middle section is topic representation B and all of the sub-iterations below that. So that tends to perform in overall a little bit better than the others. So this is the case study representation. And then the other thing to note is you can kind of see their little blocks of 4 where the median lines don't really change. So we didn't see a lot of variation. Those are the retrieval models, and we saw probably the least amount of variation across the retrieval models. And then I flipped it around. So these are 56 topics, or 56 box plots, one for each of the topics, and then it's the distribution of performance across the 48 iterations of the word-based queries. So this is ordered by the median value. You can see there's a big range in performance. And then, overall the performance is fairly low for the word-based queries. So most of the medians are below 0.25 BPREF. And then the other thing that's interesting is that there are some that have huge variation across the parameters and some that don't. So that kind of sparked some interest in, can we tease out, some structural components of those queries that point to certain parameters that work better than others. And so now this slide is getting into the comparison with the Boolean queries, which are the gold standard. And again, those are all handwritten, very time-consuming, and the word-based queries are all automated and purely word-based queries. So the blue line, this is precision, which is the percent of what's returned that are judged to be relevant. And the blue line is the relevance of the word-based queries, and the red line is the relevance of the Boolean queries. So you can see there's a better performance from the Boolean queries. This is in this case, since we didn't judge all of everything returned from all 56 topics for the Boolean queries, we just looked at the overlap between the Boolean query and the judged word pools, if that makes sense. So that's how we got this statistic. We just looked at the precision in that pool. And that there's only a single data point for the word-based queries because this is the precision of the actual judged pool, which is a random sample across all 48 iterations. So we decided to go in and pick 10 topics and do full judgment of everything returned by the Boolean queries and then compare that to the distribution across the word-based query parameters. And so the red triangles, which look like hearts kind of, are that's the performance of the Boolean query, and then I went back to the distribution of precision for the word-based queries. And again, there's better performance, which is what we expected in this case. So the last slide, so this is the query taxonomy, and we did several things here, but these are 6 characteristics. These are binary flags, and these are all attempts at capturing different aspects of structure in a topic. And temporal is that there's some sort of time-based sequencing in the topic, like order of events is important. Text is actually that the topic can't be represented strictly by structured data, that it also requires some text, and that really applies to semi-structured. Medication is that a medication, was required for the topic. Procedure is some sort of procedure is required, either surgery or a lab test. And additional is that additional values were required, so the lab test values would have to be checked for this topic. And then condition is that that an actual medical condition was required in the topic, and not all of them required medical conditions. Some were just screening exams. So this is change in BPREF, or the impact on performance that these different flags have or components have. And we did this, we trained the model with our actual data, a beta regression model, but we predicted on simulated data, which had every possible combination of the 4 parameters, 4 word-based query parameters and these 6 flags. So the main takeaway is that increased complexity generally decreases performance, except for text, which was interesting and kind of unexpected, that the presence, the requirement for text in addition to structured data sort of improved, those topics tended to do better. And this is all word-based query. And then I won't go into this, but this is the last figure, and I'm we were trying to get it at an interaction, which is really the goal of the model, an interaction between those 6 flags, which are on the column on the right, and then the 48 parameter iterations, which are along the bottom. And you can see the flags are 1, 0. That's all possible combinations of the flags. The only point here is that there are obviously patterns. This has been clustered that sort of match certain parameters, do better with certain combinations of these flags, and that could lead to something in the query guiding what method is selected. That's it.
Is this the clicker? So I'm going to back up a little bit and talk about why we do all this for a minute. So there are over 1,200 rare disorders known in the world. A rare disorder is something that affects less than 1 in 200,000 patients worldwide. As you can imagine, because they're rare, people don't think about them, and they are highly underdiagnosed. One particular rare disease that we looked at for this work is acute intermittent porphyria, which is a genetic disease which causes mistakes in heme biosynthesis, and this affects like 5 in a million patients worldwide, right? So we're talking really, really low prevalence. But patients that have the disease, there's a significant, morbidity. There's a significant effect on their quality of life. They have intermittent, but sort of constantly intermittent, if you will, keeps coming back and back and back. Neurovisceral symptoms, including abdominal pain, nausea and vomiting, weakness, psychiatric changes. To make this even more tricky, there's variable penetrance. People can have the genetic defects and not really have the symptoms. So to be diagnosed, they actually have to have the symptoms, they have to have the genetic defect, and they have to have a positive test. And there is a definitive positive test for AIP, which is an inexpensive urine test for porphobilinogen. I can never say this word, and Bill's laughing at me. I just can't say it. But it's that thing that's spelled out right there on the slide. Now, maybe this didn't used to be as big a deal because the treatments were not very specific in the past, and I guess they did help some. But now, with more advanced research, there's like RNA silencing treatments and things like that that are really very effective. They're also very expensive, but they're really very effective. So now, delaying the diagnosis of these patients for years because they have these sort of general symptoms that overlap with other things, and they come in and they think it's one thing, maybe they think it's irritable bowel and it goes away, and then they come back and they don't get diagnosed for years and they're suffering with this and they don't really know what it is. Now there's treatments, and it's important to identify these patients sooner and get them treated so that they have a better quality of life. So, the question is, this is the 21st century. We have EHRs, we have all this data. Can we practice some kind of 21st century medicine and use all these tools that we have to identify patients that are needing to be screened for these rare diseases? And in this case, what we studied was this particular example of acute intermittent porphyria. So can this be done, right? We can't screen everybody. The screening test is cheap, but we can't screen 1 million people, right? But we can screen 100 people. We can screen maybe 1,000 people. We'll see. So how do we do this? We actually expanded the data set that Bill mentioned, the original data set that was used for the information retrieval. That had 100,000 patients. We updated it to, it's actually 220,000 patients. And we got a new pull of this. So it had, updated ICD-10 codes and a number of things that were not available when the original pull was done. And in addition, we enriched this with all the patients that we could find that had any mention of porph in their diagnosis or their lab test or their notes or anywhere. We don't think these patients have porphyria, by the way, at least not most of them. We just wanted to cast as wide a net as possible with our original data. Bill showed you the diagram of basically the different document types. It includes notes, includes medications, includes lab tests and things like that. And each of these we wound up treating as a different document type. And we divided the patients into cases, the positive cases and the negative cases. The positive cases were the patients that had E8021, which is the specific ICD-10 code for AIP. And not every patient that has that in their record actually has AIP. We also did manual review, and we wound up with 30 positive, manually confirmed cases of AIP, and all the rest of the data, 220,000 patients minus 30, is the negative training set. We're assuming that for the purposes of building a model that they don't have AIP. We'll get to that in a minute. So what was the approach? Very, very high level, because I don't have a lot of time to get into this, but we parsed each one of those documents, each record, into different features, and we labeled each feature by what document it came from, because if an ICD-10 code came from a problem list, that's different than if it comes from a visit code. So we labeled all the features with where they came from. We scored it by the frequency of appearance because we were looking at their medical records longitudinally. So we wanted to know, for example, did somebody have a chief complaint of abdominal pain once or 20 times? That turns out to be relevant here. And what we did first, remember, we've only got 30 positive cases. We've got 220,000 negative cases. And we have lots and lots of features that are very specific to porphyria. The note could say patient has acute intermittent porphyria. They could have the diagnosis code. They could have, there's a specific treatment called Heman for acute intermittent porphyria, which could be part of their record. All of these are giveaways. And if you're trying to score a lot in a machine learning contest, that would be great because they're good clues and you can find these patients. But that's not what we're trying to do here. What we're trying to do here is we're trying to find patients that should be suspect of having acute intermittent porphyria and aren't. So we're trying to look for features, these generic symptoms and generic patterns of care that are associated with maybe needing a porphyria test that they didn't have. And we're not, for the most part, that interested in patients that the medical system already has suspicion that they have porphyria and has already given a test to and has already followed up. So what we did was we took all these features, we scored them, and then we did a univariate analysis on all these features. I can't remember how many, 1 million features, something like that, including all the bigrams and unigrams that we parsed out of all the notes. And we did a number of filtering processes on those features, looking for things that occurred in a sufficient number of records, that had a sufficient a statistical p-value, that had sufficiently high odds ratio in terms of predicting the 30 positive cases that we knew about. And we wound up with, and then we sort of took, I think, the top 100 from each document type. And then we went through those manually and manually removed features where it was obvious that there was clinical knowledge that the patient had porphyria or was already suspect for porphyria. So, we took away all the obvious stuff. We took away that they were treated with Heman. We took away all the ICD codes that were directly associated with Heman. And we wound up doing this kind of in an iterative fashion because the more we looked at it and the more we sort of tracked down what some of the codes meant, because some of these codes were very specific OHSU lab codes and things, because that's how they show up in our data. We had to drill down and see what they meant and see if, well, is that really associated with suspicion of having porphyria, or is that more of a general thing? So, the lab test for porphyria, that word, we took out. But the fact that they had many urinary samples, we left in because that's sort of an indication of how many times they were intersected with the healthcare system and how many times, it was thought to check their urine, even though they didn't check it for porphobilinogen. And then we did a number of different kind of model creation. We chose to use the SVM with the RBF kernel, basically just based on using cross-validation with the data that we had. And we built a final model using all the data, and then took that model and applied it back to all the negative patients, scoring all those negative patients. Now, normally you'd kind of think that that'd be highly biased, but the thing is we only wound up with about 100 features. There were only 30 positive cases, so most of the negatives didn't really participate very much in creating the support vectors in the support vector machine. So anyway, we wound up with a score across all the patients who were thought to be negative, and we can rank those patients by that score. Then what we did is we did some filtering, and we actually created 2 filtered sets to manually review, but I think I'm only going to talk about one set here. So what we did was we filtered out anybody that had a porphyria diagnosis, anybody that had a urinary test for porphyria, and anybody that had mention of porphyria in a note. So we really wanted these patients to be ranked that had no suspicion, essentially, documented in the chart of porphyria. And then we applied our ranking to them, took the top 100, just it's 100 because that's what Steve could manually review. Steve manually reviewed the charts and came up with, essentially 1 very likely case, 3 likely cases, and 18 possible cases. So that's 22 cases where one would think it's worth suggesting that the patients have this simple urine test, right? What you would think, the natural prevalence, based on what I told you, 5 out of a million, in 100 you'd expect, 5, what is that, half of a thousandth of a case. So if this is anywhere near suggestive, it's a very powerful way of narrowing down what patients we should really focus on for something like this. We would be, really excited to find 1 or 2 positive tests out of these patients. Okay, so what are the next steps? We're going to follow up with this by doing a little mini clinical study that I think we're about to get the IRB approval for. It's just in the last little edits. But basically the way we're going to do this is we're going to contact the primary providers of those patients where we think it's useful to have the urine test, and we're going to tell them that we had this computer model and went through all the patients in their history, and we identified their patient as not having one of these tests and having symptomology that is compatible with porphyria, and they should consider giving the patient this test. And if they want, they have a local disease expert, Tom Delary, who is an expert in porphyria, and he's available for consultation either with the clinician or with the patient if the clinician thinks that that's relevant. And then we're going to just track this. We're going to see how many tests get done, how many are positive, what the natural history is of these patients, and hopefully we'll be able to find some patients who are undiagnosed and do some actual medical good with all this. So that's it, right? Next slide. Next slide is Steve's. Yeah, here you go. Yes.
Okay, so future directions with all of this stuff. We started doing this work under an R01 that we had with Mayo Clinic. It expired, and we submitted or is sort of basically expired, and we've submitted a renewal to continue this work. And all of the things that Bill and Steve and Aaron have talked about continuing forward are part of it, but we also have some new IR and machine learning that we're going to have be part of it as well. And sort of the argument that we made to the NLM was that one of the things that we learned from doing this and from other projects is that patient retrieval for cohorts of EHR data is just fundamentally different than traditional document retrieval, which as in looking at it from a IR standpoint. It's just a kind of a different animal. The traditional way of doing IR and sort of to a rough approximation, natural language processing for sort of document classification and scoring is you find some way. Does this thing have a laser pointer? You find some way to take a document and make a representation out of it, and that could be a list of the words that occur in it. It could be some kind of vector space representation, lots of different ways to do it. You do the same thing with the query, hopefully in a way that's comparable. You come up with some way to compute that score, and there's about a million different ways that one could compute that score. And then you score all of your documents against a query, and you pick the ones that have the highest score, right? And that's sort of like the general high-level framework. And in practice, traditionally in IR, we would have used bag of words approach, right? Just list of words. And I kind of touched on this. I'm just going to skip that. That's the traditional way. For patients, though, that's tricky. So the document we're talking about is an entire patient, right? And there's a lot in a patient. Bill had that figure that we're going to revisit in a minute. Different patients are very heterogeneous from each other just in terms of what the data looks like. Some have a lot of data, some have very little data, some of them have a ton of medications, some have no medications. And those differences are often what we want to capture, but the process of smushing a whole patient into a single representation is a very lossy way to do that. We lose a lot of information. Within a patient, there's often a lot of heterogeneity in ways that are important. So Steve touched on the different dimensions of the queries and highlighted that some queries care a lot about medications, some queries care a lot about temporal things that happened. Did X happen before Y, right? Again, taking a whole patient, smushing it into a single representation, often, especially doing it in a general purpose way that will work for a lot of different kinds of queries, erases that information. The queries themselves are very different than sort of traditional search queries, right? What car should I buy is like a nice short little fragment, or what diseases are caused by drug X or cured by drug X, kind of a nice, reasonably structured thing. The topics that Steve talked about are these very long, involved, patients who had one of these things, but not one of those things, who had them before this thing happened and then had a bad effect of this other thing, right? So very long, involved queries, and then again, the temporal dependencies. All of these things make the kind of traditional approach to query and document representation not work. Heterogeneity, just to make that a little more concrete, we saw this figure of a sort of prototypical patient with like a really rich, deep record of all these encounters of different kinds. Some patients look like that, patients who've had a lot of things go on or who we have a lot of data for over a long period of time, or both. Other patients look more like this. And if we think in terms of sparsity, right, from a machine learning standpoint, this is a much sparser record and a much sparser note. So the same approaches might not work. A approach to applying modern machine learning to patient retrieval has been to make what are called patient embeddings. This is like a slightly fancier way of smushing a whole patient into a single embedding. There's a whole variety of approaches. Typically, the way they work is you kind of sort of split up a patient into a few different dimensions you care about: demographics, medications, diagnoses, some representation of the note text. You learn a separate representation for each dimension of the patient, then you smush those together into a vector, and then you do machine learning from there. And that has actually, and you can do that representation in different ways. Here I'm showing using recurrent neural network architecture, but you can do it in any way you care to think about it. It's a very flexible framework. It addresses some of the problems that I've mentioned in terms of, it's better than just taking like all of the text in the whole patient record and treating it as a bag of words for traditional retrieval. But it doesn't take into account any of that nuance and doesn't really handle the heterogeneity. If you have a patient here with 1,000 medications versus one medication, that medication representation, you'd need to find a good way to do it. So what we're proposing to do is to explicitly capture temporal features of encounters in patients. We're going to learn encounter-specific embeddings that might look like what I just showed you, but they'd be for one encounter, right? They'd be focused on capturing what is happening with this patient at this point in time, and then we're going to explore ways to compose those together into richer patient-level embeddings in a way that lets us explicitly encode time into it. So hopefully it will learn to represent, that a patient who had A happen before B would look different than a patient that had B happen before A. Is sort of the idea. We don't exactly know how we're going to do it, but in the grant we laid out some ideas that hopefully are reasonably sound I guess we'll find out if we get the grant or not, and go from there. And then once we have these, we are going to use them in retrieval, and we're going to use them in a slightly different way than things typically get used. So using these sort of dense neural embeddings for retrieval often follows the same kind of simplistic scoring approach. People use like a traditional cosine similarity or some other kind of similarity metric between your query and your document. And what we're proposing to do is, because so many of the queries have explicit temporal dependencies in them, we're going to use an attention mechanism, which, if you're not familiar with that, I can't describe it in 5 seconds, but I'll try. The idea is when you have input that has multiple time steps to it, it's a way of having a neural network learn which time steps are important for satisfying a particular query. It's frequently used in machine translation to help with word reordering, and we're going to try applying the same thing to retrieval. So that's our sort of computational next step with all of this, and we'll see, many of the things that Steve identified in his analysis of the topics, and that Aaron identified as relevant features on the Porphyria work. We think we can use that information to help us train these monstrosities of networks, by coming up with new kind of training strategies that take that into account. So I think that's all we had. And
okay, that's the gist of what we've done. We tried to finish early enough to open the floor to any questions or comments. Actually, and let me make the comment too that well, there's actually we actually have a score on the grant, and it's potentially in the fundable range. But this project actually is going on, and there's opportunity for students and others to get involved as well. So feel free to talk to us if you're interested. But let me open the floor to questions, comments. Whoa. Okay.
It's a great project. So I had a question about the validation of AIP, maybe for Aaron. So I think there were 22 or something people that possible, probable, and possible, probable, and very likely. And I was curious to know, are you planning to validate just with the traditional clinical test for AIP, or perhaps casting a wider net for something that doesn't fit the exact classical presentation of AIP? Because from my vague recollection of porphyria, it's kind of like a whole group of illnesses, and I would still think that the approach would be useful, even if the outcome isn't that say none of those patients are actually diagnosed with porphyria in the end. Perhaps they have a very similar genetic mutation that just manifests slightly differently, and what your plans are for doing that final test.
Yeah, that's a good question. I mean, the model is really specific to AIP, meaning that that's what we trained it on. We don't have any real good reason to think how it's going to act on different porphyria variants. Certainly given, I think, the clinical review that Steve did, they need the urine test as a diagnostic, right, to know if they have that particular disease. I mean, depending on how excited the clinicians are about this and how much they want to collaborate with us and with Dr. Delary, I would be delighted if that motivated them to, drill a little deeper into, copoporphyria and some other porphyria variants, other mistakes in heme metabolism and all that. I mean, I can't say that we have any particular data from this algorithm that it particularly helps with that or not, but yeah, you have patients with weird recurring neurovisceral symptoms that, as far as we can tell, don't have a definitive diagnosis in the chart, and if this motivates them to look a little more broadly, I would definitely consider that to be, a win, even if we don't, confirm any AAP cases. So.
Cool, thank you.
And it's not, unlike a lot of machine learning that's totally unexplainable, there's a little bit of explainability, but we're actually not, we're really, turning the record into a big vector and finding other patients that have no mention of porphyria but are otherwise close to it. I mean, there could be, in fact, maybe some of the methods that Steve talked about, kind of drilling down, may be helpful. And, as over time, as we get more resources, judge more patients, we can actually test out these models further and see how they work. So I think Lily had why don't you hand the microphone to Lily? Oh.
Hello. So this was all really interesting. Thank you. What is the distinction between this tool and the existing I2B2 cohort discovery tool? I assume that it's that this tool's on the front end versus I2B2 cohort discoveries on the data warehouse side, and also is anonymized.
Yeah, I2B2 is really an interface to an underlying database, which could be our database. I don't know how our I2B2 instance works, but I2B2 also only gives you counts of things.
Right.
So our programs that we've written, go into that data and process it a lot deeper. At least that's my understanding. I don't know. We have an I2B2 expert here.
Oh, I was just going to say, you can grab, through Octree, you can grab the patient demographic data sets for those patient counts. But if memory serves me correctly, it is based off of the research data warehouse, which is coming from OHSU's instance of Epic and Clarity. So it's technically still coming from the EHR. It's just been classified out to the process to the research data warehouse and classified.
My understanding is that the I2B2 tool, at least the way we have it set up here, is structured data only. So it's not doing anything with the notes or mentioned or anything like that. It's pretty much a big Boolean query tool on the structured data in the database. So it probably does correspond to one of the approaches in Steve's graph of all those different approaches, but the approaches that the group is using are much more numerous and some of them a lot more sophisticated, and they're also looking at the text. So the I2B2 tool is sort of like baseline patient cohort identification tool with structured data, and this work is more about how can we push that field forward.
Yeah, so we have a whole bunch of people here, so keep going. Yeah, go.
So I was wondering, with the features that you did identify for the porphyria part of the project, how much did they differ from features that would have been selected by talking with clinical experts, or how much overlap was there? So was the machine learning process really finding something new and novel?
Yeah, that's a really good question. I didn't have time to go into this, but that iterative process that we talked about did involve talking to people with clinical experience. So, and we had to do that sort of feature editing removal process to get rid of the stuff that the clinicians already knew. So what would happen is that we would run the model, and all this stuff would pop up as highly weighted features, that clinicians already knew about, and that wouldn't help us to discover any new patients because they were very focused on the ways that physicians would treat or document patients that already had porphyria. And there was actually one case which is really, really interesting. I'll tell you two things. One thing was that the number one positive predictive feature was recurrent bouts of unexplained abdominal pain. Basically the ICD-10 code for that, for a number of episodes or visits with that. And the other thing that was really interesting is that we thought we made an interesting discovery because we found that another strong weighted feature was cimetidine, that it seemed like there was a disproportionate amount of being treated with cimetidine for porphyria patients. And we're like, oh, we go talk to Tom DeLaury, who's our hematology expert. And he's like, oh, yeah, we use that to treat the, to treat, I didn't know this, but we use that to treat porphyria because it blocks, one of its side effects is blocking one of the pathways, and that improves their symptoms. So we pulled that out of the model, even though that was, you know, a pretty positive predictive feature, and it was a discovery for us, you know, because we didn't know that. So it made us feel good that we were like on the right track, that we were discovering things that we didn't know, even if the clinicians did know about them. The other thing I would say, and this is definitely true in any kind of sort of clinically related informatics work, is I don't think we would have accomplished the same thing if we just talked to the clinicians and asked them what to use as features. It's much different thing saying, well, what features should we use? And they're saying, you know, heme and D20 and these different things that, you know, they use to treat porphyria patients. It's another thing to come to them with a list. We did this statistical analysis. We've scored these features with these models, and this is what we're finding. And actually, they didn't think to tell us about cimetidine. We had to bring it to them and for them to say, oh, yeah, that's right. So it really is sort of this iterative, you know, machine and knowledge engineering process to get to the point. The features that are left in the model, some of them are pretty straightforward. There's a number of things that are different ways to treat pain. There are some things that have to do with psychiatric symptoms. There's abdominal pain. And then there's weird stuff in the model that I don't know why it's scoring it positively. General lab tests, like I think getting a CBC more frequent than the background is, which may be just a, you know, an indirect indicator that they show up to the emergency room a lot, you know, that kind of thing.
Good. So someone have the microphone over there?
I essentially have the same question. Did you discover any new risk factors that we wouldn't have normally thought of? So you answered that. I just want to say as a clinician, this is one of the more exciting new uses of kind of big data for clinically relevant issue. So, yeah.
One other, I was thinking as Aaron was talking, one other thing we also pulled some OHSU specific thing, you know, like for example, the name DeLaury, because Tom is the doctor of many of these patients. That's a highly predictive, but it's completely. But we got to get rid of that. But it, obviously, if we were going to apply this outside of OHSU, I think. Do you want to ask something, Adam? Or, oh, okay, or okay. Here, I don't know who.
Yeah, I had a question. I don't know. This is going to come out kind of strange, but like for some of these like very rare diseases, if you were to like extend this model to other sort of rare diseases, would you did you have patient names available? Like I would imagine like families that people who don't know each other, perhaps in a given like for a particular medical area, say you did like, you know, Greater Portland area, et cetera. Like, is that something that would come up in your design of this model?
It could, probably not with this disease because of the variable penetrance and the way it presents. There's other diseases that we're looking at where, you know, like if you find one patient at the family, they probably all have it. And so we'd have to take that into account more. I mean, and you could either do it forward in the process or backward, right? Backward being you discover a patient and then you essentially recommend to their family physician that they do some sort of family genetic counseling or family checkup.
Yeah, I was more thinking the reverse. Like you have a patient who like you actually knew that, or they had a relative that's in the same like training set or in the data set who had the disease, but they don't know that they're related to that person, but perhaps they like, are their names happens to be the same last name, or there was some other like closer connection.
Once we've sequenced everyone. Of course, it has variable penetrance, so the
it's not perfect,
variant
but
won't
it's
be
the
enough.
higher probability.
Very little information in the EHR that I'm
For
aware
family
of
members.
tells you that people are related. Yeah, they might have the same last name.
That would be the only one I could
know, but
some vendors explicitly monitor that in the EHR. Cerner.
if it gets entered. True. I mean, the thing, yeah, the EHR has a place for everything. finding.
it's used. Yeah.
Right, exactly. But, you know, you might discover this, you might discover clusters of
Cool.
people and, you know, want to do something with that, and that would probably be sort of a more detailed version of this first, you know, kind of clinical study that we're doing by emailing clinicians. You know, we may, in the future, want to include some kind of follow-up with that. It's a good idea, actually.
Really interesting talk. And so my question was just kind of scaling up to all the other rare diseases. Do you kind of envision this sort of approach where you're doing feature engineering, you know, consulting with physicians, removing features that are actually indicate that there's been a diagnosis? Do you kind of envision that to be the model going forward, or does some of the things that Stephen, that you're doing, could you have more of an automated feature detections as part of the pipeline?
I think it could be both. I like to, my own personal bias is that doing something more handheld and manually the first few times to really understand the problem space generates value as it is, and is a good way to prevent making bad mistakes when you're doing something blind. But I also think that in the long run, maybe not for the first set of rare diseases, but eventually, that, you know, some of these deep learning approaches, especially if we intersect them with, you know, learning from medical sources on, you know, treatments and things like that, to remove those things as too obvious indicators. You could conceive of how you might be able to automate this on a large scale in the long run if you really wanted to. Right now, I think we're really focusing on, okay, well, what are the rare diseases that that have a high value proposition, at least as far as the patients go, you know, that where you want to discover them, they're underdiagnosed, there's a good way to treat them so that there's some value to the patient in that, and they can't be so rare that it's unlikely you're going to find any of them, right? So something like that. But yeah, I mean, I think in the long run, and maybe going beyond rare diseases, going, you know, more proactively in general in whatever 21st century digital medicine is, you know, I mean, there's lots of things you could do that, you know, aren't directly this work, but related to this. You know, you look at people's weight curves or whatever, you know, over time, and you're just more predictive about intervening with them based on, you know, looking at the EHR from a sort of longitudinal kind of point of view. So, I mean, I think that kind of stuff can be learned as we get more experience in how to do it. I don't know if you want to add anything.
No, just that I think one of the things something I really value about the way you approach this was with the explainability and transparency of being able to look at those features and make sense or not. Yeah. And that's a real shortcoming of most sort of more modern deep learning approaches. It doesn't really have that. You know, right. You want that, you know, do a lot more work and have a lot more data.
And this is a comment, I think, as we look at some of these methods that you're proposing, we're also going to have to kind of complement them with, like, representing time explicitly in a more explainable model. And because the deep learning really has to have a pretty big performance advantage to make it worth losing the explainability and that sort of interaction kind of with the clinician.
No, I do think if we had a really good, robust encounter or patient representation, I feel like that would augment your methods really well. Like that could be an additional input to the SVM, or that could be an additional thing to identify subpopulations that might be influential. I feel like there'd be a lot of synergies there together.
Yeah. So, Vishnu and then Nat. So.
Yeah, sure. So I had a comment and a question. The comment is that it's really exciting to hear this, and thank you for sharing this research, because clinically, the mentality is when you hear hoofbeats, look for horses. And so, you know, from a clinical perspective, if somebody comes in with intermittent abdominal pain, porphyria is one of the last things on my mind. And having this kind of augmented brain, to borrow a Larry Weed expression, which is actually, you know, using machine learning to look for zebras and present those zebras to me to kind of counteract the way that I think is really exciting. And I think that's going forward in medicine, that is something that is going to be really useful to clinicians. the question that I had is, I'm really interested in seeing what the clinical results of the 38 people that you actually pulled, when they do their tests, how many of them actually have porphyria. And exactly. And the reason is because I think this creates a really interesting paradigm to medicine, which is that as a patient, they come to me, I don't diagnose it, I don't even think of porphyria, and then they get, a letter from OHSU saying, by the way, the research has shown that you may have this really rare disease that you need to get screened for. And so as a patient, I Google it and I get into a panic, and then I watch The Madness of King George and I get into a bigger panic, and then I actually show up to have this test, and if it's positive, that's fantastic. But if it's negative, I wonder what the reaction of patients and what you guys think the reactions of patients will be.
We're going
Eventually.
to their physicians.
Right. But as this technology matures, my worry is that there's going to be a cohort of false positives that will come out of this invariably, and is that another legal risk thing that medicine has to take into account because of this kind of technology?
This is only suggesting, and we're very, explicit with the IRB that we're going to notify their physicians. We don't want to go straight to patients. So basically the physicians will get an email and offering more information if they want. They'll be able to contact Tom DeLowry. But so the 21st century analog is when the 20th century is when you hear the sound of hoofbeats, think horses. And the 21st century, it's when you hear the sound of hoofbeats, run a machine learning algorithm, right? So, anyways, Nat's been waiting, so he'll be the last question. Can you hand him the mic, Aaron?
Thank you very much. It's a really interesting field in research. I have sort of two-part questions, sorry. But the first part is, okay, if you're focusing a lot on the symptoms of the patients when they come in, a lot of that information is hidden in free text, essentially. And there's a whole debate about how to parse that out accurately. And so first of all, how you deal with that. Second of all, if you're focusing more on the diagnosis part of the part of the medical record, do you have to have you ever run into issues or being able to find out if there's cluster of diagnoses that point more toward AIP compared to, if you have that cluster of diagnosis? Because a lot of this thing in medicine we do differential diagnosis, things that are related to each other and could be possible explanation for the condition. Have you seen those clusters coming in? Like people who are not being diagnosed for this for AIP have this cluster of diagnosis, essentially, when you were looking through the data.
Yeah, I mean, remember, we're actually not really parsing we're not really parsing out down to understanding what this disease is. We're basically representing the whole record as a vector, and we're trying to find other vectors that are similar to it. Maybe we might learn that there are actually, better approaches to do that. Maybe if we selectively apply NLP or something like that to specific pieces, or maybe these word embeddings might help with that. But for right now, our approach is really just to look for kind of global similarity across all these features.
For precisely the reason that you identify, right? Yeah. It's very, very hard to extract all of the information from free text in a sort of structured, rule-based way. Very, very, very hard. So what turns out to work a little better for some things anyway is to just kind of come up with a representation of a whole node, train a machine learning model generate the representations in a way that preserves the information that you would have hoped to have gotten if you could have parsed it all out as well, right? And then go from there. So for certain applications, you actually do need to go all the way down and parse out specific pieces of information of the node, but that gets to be already. Well, there's a whole field of computer science, right?
So you have anything more to add?
Well, I would just say again, to do the simplest thing possible first. I mean, we did parse the notes down into unigrams and bigrams, and some of those did represent symptoms, and they did pop up. Again, probably the strongest thing is recurrent episodes of unexplained abdominal pain was sort of the pattern, I think. And then, other kinds of psychiatric manifestations would add to that. And it seemed like that there were some patterns in the pain being treated with some drugs as opposed to other drugs being relevant to identifying patients in their, with their emergency room visits. But, that was sort of observed afterwards. We didn't feed that into the model. We saw kind of what the model tended to focus on. So there's lots of ways of doing it. There's lots, creating these general patient representation vectors, may actually help, represent things at a more at a higher and less particular level. Like when Bill talks about representing these patients as vectors, these are big vectors. These are like vectors with like 1 million dimensions in them, and most patients are mostly zeros in those vectors. So, having less of a sparse representation, more of a dense representation might be advantageous. The problem is those dense representations are a little less easily explainable, what they mean and why two patients are like each other or whatnot. So, this is why it's research. And we'll investigate these things and we'll tell you what we learn.
Great. Okay, well, thank you, everyone, for your comments. And